1, 0.
1, 2, 3, 4.
Hi everyone, today we're going to do section 6.4, graphing basic trig functions. So we're going to take a look at how to graph sine, how to graph cosine, and we might get to graphing tan, but I think we're going to save that for part 2. So if you look at the cover of your package, you'll see that when it says, what's your sine, there's a graph. And it kind of looks like that minus the x and y axis there. And basically we're going to see what it looks like when we take our unit circle and we unravel it and we put it on an x and y axis. So to begin with, we're going to take a couple basic points here. So we have what would happen if you sub in 0 for x, pi over 2, pi, 3 pi over 2, and 2 pi. And we get some of these key points here for sine x. So imagine this, if you had your unit circle, let's draw this again right here, and we'll just quickly label the quadrantal points. So we have 1, 0, 0, 1, negative 1, 0, 0, negative 1 right there. Okay, so if we were to take a look at that and you were to say, well, what would happen if I was to find out what my y values would be, because we know that sine was equivalent to the y values from our previous lesson. What would happen if you had something that said sine of 0 or sine of pi over 2 or sine of pi and so on? And so when you looked at sine of 0, you could start right here and you'd say, well, the y value there is 0. And then you could continue on and you could say, well, sine of pi over 2 would give us a value of 1. And sine of pi would give us a value back at 0. Sine of 3 pi over 2 would give us a value of negative 1. And sine of 2 pi would be back at 0. And so what starts to happen is you have these key points, and we're going to start to plot that on an x and a y axis. So what they're saying is when your x values are represented by these top values here, they're going to pair up to create full coordinates with these y values here. And so what emerges is you'd have the point 0, 0, and the point pi over 2, comma 1, and the point pi, comma 0, 3 pi over 2, comma negative 1, and 2 pi, comma 0. So down below here, you can see that there's a grid. And before we fill in the second part right here, let's see what would happen if we start to plot these points. What would everything begin to look like? So taking a look over here, I'm going to label this at 0. And what we'll do, and we'll talk about this a little bit more in detail as we do a few more examples, is every 3 spaces, I want you to list as half a pi. So 3 spaces, pi over 2, right here's pi, 3 more spaces, 3 pi over 2, and right here, 2 pi. And for the sake of this first graph right here, so we can see its shape, we'll do this in quite a bit of detail. We'll say going up 2 units will represent 1, and going down 2 units will represent negative 1. So if you're to graph the points that we just talked about, and you're looking at your chart right here, we had the point 0, 0. We had the point pi over 2, 1. We had the point pi 0, 3 pi over 2, negative 1, whoops, and 2 pi, comma 0. And that's going to start to give us the shape of what a sine function could look like. And in most cases, this is as much detail as I would ask for, but because we're doing this for the very first time, we want to look in a little more detail. So I'm going to explore what happens for a specific part of graphing the sine function. So right here, you could draw out your special angle triangles and we could find out what's happening at pi over 6 and pi over 4 and pi over 3 and so on. And let's do that right now. So for pi over 6, that's, again, remember the equivalent of having a 30-degree angle, and you have 31 root 3, and 2. And if you're to graph sine, you would say, well, sine would be opposite over hypotenuse. That's going to be 1 over 2, and you get something like that. And then you could say, okay, I'm going to draw a 45-degree angle for pi over 4, and I have a 1, 1, root 2. And if I did that, I would get 1 over root 2 right around there. And then you could say, okay, I'm going to draw a 60-degree angle here for pi over 3, and you get 1, root 3, and 2. And if you did that, you would say sine, so opposite. Okay, you get root 3 over 2. And you could continue on with that. So as you fill in the rest of this, and I know we've done this from previous lessons, you do get something that's symmetrical for 2 pi over 3, and then 1 over root 2, and then back at 1/2. And so those would be the values that you would end up getting if you did the details for all of those. So what would that look like if you were to plot these points now on the same graph? Meaning that this is still your x value, and you're going to pair it up with the 1/2 y value to create another point. So for instance, you'd have the point here. This would say pi over 6 comma 1/2. Okay, and so if you're to do that, we can now revisit why we said every 3 spaces is going to represent half of a pi. So if you think about what we did is, if you're to talk in degrees for a second, if every 3 spaces is half a pi, that means that every 3 spaces would be equivalent to 90 degrees. And that means that every 1 space would be equivalent to 30 degrees. And so if you're to say, what would that mean if this was over 30 degrees? That would mean that this here would be a pi over 6. And 2 spaces over from the point 0, 0 would be at pi over 3. And when you do that for the first time, you might say, hey, this is kind of weird. We went from 0 to pi over 6 to pi over 3 to pi over 2. But if we now look at what everything could look like with a common denominator, you could say, well, this first space is really just saying I have 0 pi over 6's. And then this is saying I have 1 pi over 6, and this is like saying I have 2 pi over 6's, and this is saying I have 3 pi over 6's. So every time I move over a space, I'm moving over a pi over 6 increment. And you could continue that all the way through. And so right here, our next space to the right of pi over 2, you could say, well, that would be the equivalent of saying that's 4 pi over 6. But instead of saying 4 pi over 6, we know that instead of having to do that, we could say, well, 4 pi over 6 is equal to 2 pi over 3. And 5 pi over 6 would be right here. And then 6 pi over 6 could be reduced to just pi. And so if you're to now say, well, that's going to help me label these points because I know I have the point pi over 6 1/2. And that would be right here. And let's skip over to what would happen. I have the point pi over 3 and root 3 over 2 is our next space. Root 3 over 2, that's going to be something like, that's going to be around 0.86 if you're to find that out as a decimal. So it's going to be somewhere up around here, but it's less than 1. My left-handedness is showing up here a lot. And then if you wanted to put in this pi over 4 would be halfway between 0 and pi over 2. So it's actually 1.5 spaces over, and it's 1 over root 2, and 1 over root 2 is about 0.7, around there. And so what you start to get is you get a shape that's going to now look like that. And if we now quickly fill in the remaining points here, you would get something where 2 pi over 3 would still be pretty high. 5 pi over 6 is back down to 1/2. And 3 pi over 4 is at that 0.7 right there. And you get something that's not a linear relationship. In fact, we call this a sinusoidal relationship. And you'll notice that the pattern would continue on. So we're not going to do the same detail for the remaining part of it, but just you can now trust that it's going to create something that would look like that, and it's going to make this sine wave. We could continue that to the left, you can continue that to the right, and you'll start to see that you can now do this pretty efficiently, and we don't have to do the same amount of detail every single time. So I'm going to say here's negative increments. And instead of drawing each of the individual pi over 6 points, I'm just going to say right now this graph, as it goes to the left, continues to trend down. So I'm going to go down to the minimum. It's hit the bottom as low as it goes, then it starts to go up, and it's going to go up to its maximum. It can't go up any higher, so then it starts to go down right there. And what you could do is you can now just join those points pretty quickly, and you have that. So a couple things to note from this. So one thing I would say is imagine what each of the quadrants look like when you go around the sine curve. So if you have your cast and you're to draw that out, you know that sine is positive, positive in quadrant 1 and 2, and then it becomes negative in quadrant 3 and negative in quadrant 4. And what that means is when you start to graph that, it's the most positive it ever is right at pi over 2. It hits a maximum at 1, then it starts to go down to 0, but it's still positive in that first quadrant and second quadrant. But in the third quadrant, when you're from between pi and 3 pi over 2, you're negative. And the most negative it gets is right at 3 pi over 2, and then it starts to become less negative until it's back at 2 pi, which is the equivalent of 0, and you're right there. And that's what would happen as you go around the circle. And from there, I like to say it's a copy and paste function. So if you've gone around the circle one time, you can now take the part that we just highlighted and you could copy that and paste it forever to the left and forever to the right. You'll see here that we have a copy and paste to the left right here. And that'll go on and on. So when we take a look at some of these questions and some of the terminology that comes up from it, one thing that you're going to start to see now is the term period. And when you have something where you have a periodic function, that's going to be the length it takes for it to complete one full rotation. And so in this case for sine, a basic sine function that has no transformations occurring is a period of 2 pi, and that's the length it takes to be able to copy and paste it. The amplitude is going to represent the amount it goes up and the amount it goes down from the midline. So in the graph that we have right here, our midline is the x-axis, and you went up 1 unit and you went down 1 unit. And so we would say in this case the amplitude is 1. And what you can do is you can start to now say, well, how would you fill in something like y equals sine x? And so if you have y equals sine x, we just said that it goes forever to the left, forever to the right. So the domain is going to be all real numbers. The period is going to be 2 pi, and that's the distance it took from start to finish. Let's come back to the x-intercepts. The range is everything from -1 to 1. The amplitude was a unit of 1. We went 1 up in the same way that we had gone 1 down. The y-intercept in this case was at 0. And then the x-intercepts, well, take a look at the graph that you had, and the x-intercepts are occurring. There's an x-intercept at 0, there's an x-intercept at pi, there's an x-intercept at 2 pi. Well, if you're to continue on that pattern, you could probably say, well, the next one would be 3 pi, 4 pi, 5 pi, 6 pi, and so on. So it's going to happen every time that you add pi. And the way we would represent that is we would say this: x is going to equal, and they want the general solution, so they want all of these answers. X is going to equal every n pi. So it's going to equal every multiple of pi, and we'll say where NEI. So it's going to say where n is any integer. Now we know this is a bit of an awkward way of saying it. This is how we say it in British Columbia, where we say NEI, and is the element of all integers, using a capital I for integer. An international symbol would use something more like a Z. But if you think of this, we could put in a 1, 2, 3, 4, 5 pi, all of those, and that's going to give us all of the x-intercepts going to the right. And then if we put in negative values for n, you could get all of those negative integers going to the left as well. So that's how you'd represent something like that. Okay, so what I'd like you to do right now is I'd like you to pause the video, and if you feel comfortable in how sine looks, could you predict what cosine would look? So I want you to space everything out with the exact same increments that we did along the x-axis, where every 3 spaces represents a pi over 2. And I want to see if you can fill in this chart and see what would cosine look like. So pause it right now, see what you could do, and then unpause it, and let's check to see if your solution matched ours. So we know cosine is equal to the x value. And what we'll say for this is, if you're to fill these in quickly, then the x values beginning here would be 1, 0, -1, 0, 1. Okay, and you'll say this one's probably going to be a whole lot easier now that I've done one of these questions. So we said starting here, this is at 0, 0. Every 3 spaces, I'm going to have half a pi. We'll do the same spacing vertically too. That's going to be +1. Right here, this is going to be -1. Okay, and then based off of that, let's see what we could say. Um, We started at 1, we went 1, 0, -1, 0, +1. Okay, and then from there, we need to fill in what would happen for those other points. So if you look at cosine here, we have that same chart where we could draw our special angle triangles to fill in the rest. And I'm not going to do all of these, but if you did these, you could say, okay, pi over 6, we could have root 3 over 2. This would be 1 over root 2, and this would be 1/2. Okay, and then right here we're going to have -1/2, -1 over root 2, and negative root 3 over 2. Okay, so let's see what would happen. Now, the first thing is these 3 points here are in quadrant 1. These 3 points here are in quadrant 2. And so it makes sense that the first 3 points are positive and the next 3 points are negative. And we said root 3 over 2 is around that 0.866 number. So that right there was that pi over 6. This right here was that pi over 3. And we're at 1/2. And then halfway in between there, we're at, we have the point pi over 4, 1 over root 2, which is around 0.707, and you start to get something that looks like that. And then we could fill in the rest right here. So here we have 2 pi over 3, and right here we have 5 pi over 6. Okay, and I'll just do this a little bit faster now. You get something that looks like that. And again, you could trust that it's going to continue to make that shape. And this is also called a sinusoidal shape. So even though it's a cosine graph, it still makes a sinusoidal shape. Now we can quickly do our copy and paste, and we could fill in the left side by saying, let's go 3 to the left, 3 to the left, and so on. And again, we don't need the same details. So what we can do is, well, it's reached its maximum point at 0, 1. So it's going to continue to go down until it reaches the bottom. And it's going to continue to go up. So don't overthink that. We could just say, okay, here we go. There we have it. And so that's graphing cosine. And hopefully some of you are saying, that looks kind of similar to sine, just maybe it's a little bit off in terms of a translation. And we're going to start to look at that as we go through some of these examples. So the domain of our graph is going to still be x is all real numbers. That cosine is going to go forever to the left and forever to the right. The period is still 2 pi. Let's come back to the x-intercepts and let's do that last. The range is going to be everything from -1 to 1. The amplitude is still 1, and the y-intercept is this time at 1. Now the x-intercepts, this one's going to be a little bit tougher. It looks like we have an x-intercept at pi over 2, an x-intercept at 3 pi over 2, and the next one is going to be at 5 pi over 2. So the difference between pi over 2 and 3 pi over 2, if you subtract 3 pi over 2 from pi over 2, it's a distance of pi units. And you're going to have an x-intercept every time you travel over pi units. So what we'll say here is we're going to say it's going to be x equals pi over 2. And that's the first non-negative. So I want you to think about when you list your answer here, you can list it as your first non-negative answer. So x equals pi over 2 plus every increment of an n pi, where n is any integer. There's multiple ways to be able to represent that, but I think that's the most common. That's what you're going to see in Michelson, and that's what I would totally recommend. So list your first non-negative x-intercept and then add the frequency to it right after. Okay, so here's a good understanding to see, do we know how to graph sine and cosine, and can we now graph it efficiently? So if you're to graph sine, we're going to plot this right here. We're going to label, let's label our point 0, pi over 2, pi, 3 pi over 2, and 2 pi. And then going back here, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Okay, so when we graph sine, one thing that you could say is you could say 0, starts at 0, goes up to pi over 2, pi, run down there, right there. And as quickly as you can graph those key quadrantal points, you should be able to join it just like that. And then you can copy and paste it. Oops. And you get something that looks like this. Okay, so based off of that, if you're to now graph cosine, and you're to say, well, what would that look like in reference to cosine? Because we know that cosine started up right here at 0, 1, and then it had points here. And it ended up looking very similar. So cosine right here looks like it has to go through some sort of translation, left or right, and then it would be identical to the sine graph. And so it says, what is the minimum horizontal translation applied to the graph of cosine to create the graph of sine? So if I took this point 0, 1, and I shifted it 3 units to the right, 3 units probably isn't the best way of saying it. If I shift it pi over 2 to the right, then I would be on top of the sine graph. And you could probably predict what a horizontal translation of pi over 2 units would look like based off of all the transformations we've done this year. And you could say, well, that means if I had y equals sine, sorry, we want to translate cosine. Cosine of x minus pi over 2 to the right, that is going to be equivalent to the graph of sine. Okay, so let's go through some terminology now. And I know this is something that we've done so many times this year. We've transformed polynomials and we've transformed logs and we've transformed radicals. So we're used to all of the different transformations that happen. We've transformed conics. So let's see if we can now just make sure that everything here is official. So think about what your transformations vocabulary would be for these parameters for A, B, C, and D. Okay, so A here, you would normally call this is normally your vertical expansion or compression. And then it would also tell us if we have some sort of reflection over the x-axis. Your B value would represent any sort of horizontal expansion or compression, and it would represent a reflection, over the y-axis. Your C value is going to be your horizontal translation. And so that's moving left or right. And then D is going to represent your vertical translation. And that would be going up or down. Okay, so that's what we're used to in terms of our transformations vocabulary. So in terms of how we would talk about something like this, we're going to say there's some different ways of being able to express this. So our A value here, it does represent those same things that it does with transformations, but we're now going to say A is going to tell us what the amplitude is. And we'll get into that a little bit more when we look at some examples. But basically, the absolute value of A is going to be our amplitude. And it'll also tell us if we have any sort of reflection over the x-axis. Okay, our B value is going to help us find the period. So it won't represent the period itself, but it's going to tell us, if it horizontally expands and compresses our graphs, then that's going to change our period. So if we normally have a period of 2 pi and we horizontally expand it, then it's going to be something more than 2 pi. So it's going to help us find the period. Our C value is going to represent our horizontal phase shift. And then for a vertical translation, we now call this our vertical displacement. Okay, so those are some of our new terms that we have right there. Okay, so how can we find the period with this B value right here? So I want you to imagine something like this. Imagine if you had y equals sine x, and then you had something that said y equals sine 2x. So the x has been replaced with a 2x. So I would say, based off of what we learned in the past, this would mean that we have some sort of horizontal compression by a factor of 1/2. And that would mean that if I used to have a period of 2 pi, I would now have a period of half of that. I would have a period of 1 pi. And what we can say then is your period is going to be equal to 2 pi times 1 over whatever that B value is. So if this case it was 1 over 2, then that told us that you would get something that would say 2 pi over 2, and then that would give us just pi. Now instead of saying 2 pi times 1 over B, we'll just say our period is going to equal 2 pi over the B value right there. Okay, and that's going to be something that you're going to see over and over and over again. Okay, so given all of this, We have a bunch of examples now that are going to go through some of this terminology. One of the key things is just to make sure that everything is in what we'd call the ready position. So when you go through a transformation, you want to make sure that if you have to factor out a value, you factor that out ahead of time. And so here for our first graph, we have an amplitude of 2. Our period, there's nothing here affecting the b value, so our period would remain at 2 pi. That's normal for a regular cosine function. A horizontal phase shift is we're going to go pi over 2, and let's give it a direction, pi over 2 to the right, okay? And then we're going to go 1 down. Okay, I'll do part B right here, and after we've done part B, I would recommend pausing the video and then trying the next few examples if you can. So this has an amplitude of 2/3, but then I would add that it has a reflection over the x-axis. Okay, so when you list the amplitude, you always list it as a positive value. You're not going to say that you have a negative amplitude with anything. So you have your amplitude is 2/3, but it also happens to be reflecting over the x-axis. Let's come back to the period because I think that's one of the harder parts to answer. But our horizontal phase shift is going to be pi over 12 to the right, and this is going 3 up. Notice that we didn't have to say it was in ready position. We didn't have to factor out anything because they had already factored out that 1/4 for us. So I want you to think of the period in two different ways. The first way I want you to think about this is think in terms of transformations, where you would say for a transformation, that's representing a horizontal expansion by a factor of 4. And if that's a horizontal expansion by a factor of 4, then that means that your period of 2 pi would be quadrupled and you would now have a period of 8 pi. And if that's the best way to think about it, just continue to do that. The second thing you could do is you could start to use your formula, and you can know that, hey, if period equals 2 pi over the b value, and I have 2 pi divided by a quarter, that happens to be equal to 8 pi once you simplify that. Okay, so pause the video right now, see what you can come up with for part C and part D. Okay, so as you did part C and part D, you probably said, okay, this 3 over 2 needs to come out. It's not in ready position. And that means that we're going to have to factor it out. And it's not the easiest thing to factor out. Okay, so if you factor out a 3 over 2, that means you're basically going to be dividing it by 3 over 2. And if you did that, that would be like saying, I'm going to take this pi over 2, and I'm going to divide it by 3 over 2, which is the same as saying I'm going to times it by 2 over 3. And you get something that would then say, this is going to be plus, pi over 3, like that, plus 1. Okay, so if that's weird, you can always do a check. And what I mean by that is you could expand that 3 over 2 in here. You could see if you come back with your original value. So take a look at what that would be. And if you did times that 3 over 2 in there, you would get 3 over 2x plus 3 pi over 6, which reduced to pi over 2. So yes, we did that correct. So that means we have a horizontal phase shift of pi over 3 to the left. And it means that we have a vertical displacement of going 1 up. And our period, well, this one's a little bit weird. I mean, that means that we have a horizontal compression by a factor of 2 over 3. But instead of doing that, let's see if we can use our formula. And we could say period equals 2 pi over our b value, which means we have 2 pi times 2 over 3, which means our period will be 4 pi over 3. Okay, for example D right here, we have to make sure we subtract the 3 over there. Amplitude of 2. Our phase shift is going to be 2 to the right. Our vertical displacement is going to be 3 down. And then one thing that might look strange with this is you might say, well, I went 2 to the right. How come I didn't go 2 pi to the right? And that's because our period is going to be something that we haven't seen before. If you take your period and you say, well, period equals 2 pi, and you divide it by your b value, and you go 2 pi divided by pi over 6, that is going to give you a period of 12. And so you can have examples where your period doesn't necessarily have to be in terms of pi's, but it could be some sort of integer type number like 12. Okay, we're going to go through example 3 and example 4, and then we're going to pause that for today's lesson. So looking at example 3 right here, it says determine the range of the following functions. And what I want us to do with this is I want us to draw a mini graph. Let's draw a mini graph for both of these. So if we're drawing the range, we don't need to worry about the A, B, C, and D parameters. We only need to look at a couple of them. And in particular, what we'll say is this. If this is your A value, here's your B, here's your C, here's your D. We're going to say, we want to say this D value is going to represent our vertical displacement, and that's down at -3. And then from that -3, that's your new middle line. Your amplitude goes up and down from the vertical displacement. So from that -3, you're going to go up 2 and down 2 because your amplitude is 2. So you would go up to -1 and down to -5, meaning that your range for this question would be everything from -5 to -1. So when you want to find the range of a function, you have to look at the d value and the a value. So you could say we look at the da part of it. Right here for cosine, for part B, whether it's a positive or negative, there's a reflection, that actually doesn't change anything in terms of what our vertical displacement line is going to be. Our vertical displacement line is still at this +2 right up here. And from there, you go up a half and down a half. So you go up to 2.5 and down to 1.5. And your range is going to be everything from from 1.5, positive 1.5 to 2.5. You might be saying, wait a minute, I still don't understand that part where if there's a negative there, what does that mean? We'll learn that in some more detail, but essentially what would happen is if you have a positive cosine graph like this, if you now have a negative cosine graph, it's going to still have the same vertical displacement line and the same amplitude. It's just going to be a flipped version of that, but it would still have the same characteristics when trying to find something like your range. Okay, and finally, example 4 right here. Write the equation of a sine function that has each of these characteristics. Okay, so part B is in degrees, and so let's answer it in degrees. But again, why don't you pause the video right now and see what you could do to be able to come up with a sine and cosine function for this. Okay, so everything seemed pretty easy except for this period of pi over 6. How do you fill in that part right there? In the same way that you could say something like, if the period equals 2 pi over b, if you did some algebra, you could actually then also say that b is actually also equal to 2 pi over the period. And if your period is pi over 6, then that means that your b value would be equal to 2 pi over pi over 6. And then if you work that out, then you could say that would be equal to b equaling 12. So you'd have a value of 12 right here. And if you're saying that seems really strange, like how does that work for something like that? Well, think about that. It means you have a horizontal compression by a factor of 1/12, meaning that it is way, way, way compressed from what its normal value used to be. And if you think about what pi over 6 is, a period of pi over 6 is just saying I'm 1/12 of a full rotation, because a full rotation is 2 pi, and I've only gone over pi over 6. So it is incredibly horizontally compressed. If you're confused about it and you want to think about it in degrees, it would be the equivalent of saying, I used to have a 360-degree period, now I have a 30-degree period, and 30 degrees is 1/12 of 360. So I'm compressing it by a factor of 1/12. So my b value would have to be 12. And then the cosine function right here, we have an amplitude of 3. It's reflecting over the x-axis, so let's make it -3 right here, cosine. And we're going 135 to the right. If you change that to something like 3 pi over 4, don't do that for this question because we're talking about it in degrees, so we want to leave it in degrees. And then it says we have a period of 720. Again, you could use a formula, but I would almost say, well, 720 is twice 360, which means I have a horizontal expansion by a factor of 2. I'm doubling it from 360. So a horizontal expansion by a factor of 2 means I could just put a 1/2 right there. Likewise, if you did want to use a formula though, if we say normally that b equals 2 pi over b, like we did in this previous example, then you could say b equals 360 over p if you're converting something with degrees. And if our p is 720, then b equals 360 over 720, which means that b would equal something like 1/2. And that's what we have right there. Okay, I'm going to stop the video for now. I know that was a lot of content right now, so we'll just pause it right there. Thank you.